Right, today we're going to look at the rest of 0 to 5 factoring when the quadratic is greater than 1. And if we look here, one method besides slide divide bottoms up when this number in front of the x squared is greater than 1 is guessing and checking. And guessing and checking can be easier if the a is a prime number. Okay, remember prime is the only thing that multiplies to it is itself in 1. So if we look at this expression, our a is 2. The only thing that multiplies to 2 is 2 and 1. So 2 is a prime number. So here are your steps. Make sure it's in standard form, which this is. It goes x squared, then x, and the constant. Then you're going to write your factors of the first term, the a. So the only thing that multiplies to 2 are 1 and 2. And the c, the negative 12. So 1 and 12, 2 and 6, 3 and 4. From there, you're doing reverse of FOIL. So you make two sets of parentheses. And again, the reason why guessing and checking is easy here because you only have one option for the a. The only thing that multiplies to 2x squared are 2x and x. That's how you can get 2x squared. This is the tricky part where you're going to have to do some guessing and checking. You're trying to figure out what multiplies to the last term, negative 12. And then when we FOIL the middle terms, they add to negative 5. So we really have to kind of think of our ways. Like we could try 1 and 12, and that's not going to work. It's not going to add to negative 5 when we FOIL it. So the only way to get that is if we multiply the middle term. The only way we get the middle term to be negative 5x is if we multiply the negative 2x, the 2x times negative 4. So like I'm doing my I right now. Or sorry, my O right now. 2x times negative 4 is negative 8x. I multiply my inners to get 3 times x, 3x. And that would give me negative 5x like we wanted. Other little tricks along the way. You know it has to multiply be negative. So that means you know one number has to be negative, one number has to be positive. And also has to add to be negative, so that means the larger number has to be negative. So again, we have one positive, one negative in our final answer. And if you notice, the larger one is negative. If you like guess and check, feel free to use it. Otherwise, slide divide bottoms up will work. And then we're on to the prime factorization right here. Prime factorization is just basically making sure everything's totally factored. So if we looked at in elementary school, you said prime factorize just a number. So you said, all right, I'm gonna do 5 times 8. Well, 5 is a prime number, so I can stop there. And then I can say 2 times 4. 2 is prime, so I can stop there. And then I would do 2 times 2. So now I have all prime numbers. So I could write 40 as 5 times 2 times 2 times 2, or 5 times 2 to the third. Okay, that's the prime factorization of 40. Now that we're in algebra 2, we're not going to quite write it like that, but if an expression is prime, that just means it cannot be factored any further. And again, we're talking about expressions now. So if we look at our examples here, basically, bottom line, if you can factor it further, it's not prime. If you can factor it further, it is prime. So we look at number 1. I have x times x minus 4. Well, I basically look inside the parentheses. Can I factor x minus 4 any further? I cannot. It almost looks like difference of squares. It is being subtracted. 4 is a perfect square, but x is not a perfect square. So therefore, this is prime. And the reason why is because you can't factor further. If I look at number 2, I have 6 times the quantity of x squared minus 9. So I look inside here, and I do see a difference of squares. They're both perfect squares that are being subtracted. So this one is not prime. And then when I go ahead, I would factor that as x plus 3 times x minus 3. So now this is prime, and this one was not prime. If I look at number 3, it looks factored because these are all separated by multiplication. The only other thing I have to do is just look inside each factor, make sure there's no difference in squares, and there's not. So this one would be prime. Number 4, again, looks factored. However, if I look inside, Notice there's a GCF here of 2. So therefore, this is not prime. And the reason being is I have a GCF of 2. So I would just pull out a GCF of 2 for that first set of parentheses, x minus 2. And then I'd leave the x plus 7 as x plus 7. And now this is prime. And it flipped to the back end. I try these 4. All right, for number 3, we're saying, all right, there's no GCF. We're looking for SAM. And almost, it looks like it should be factored. But if I'm trying to figure out what multiplies to 9, well, I have 1 and 9, 3 and 3. I can't get any of these factors to add to 3. So therefore, this is actually prime. And it's because you cannot factor. For number 6, it's x squared plus 4. Well, I see a perfect square for x squared, a perfect square for 4, but they are being added. They're not being subtracted. And there is no such thing as sum of perfect squares. So therefore, it's only difference of perfect squares. So actually, you cannot factor this. So this is prime as well. All right. And again, for 7, prime is something you cannot factor. For 8, not prime means something that you can factor.